So what we're going to do today is continue talking about design and design process, but I want to do it in the context of actually designing things and looking at some case studies. So what I want to tell you about first is this product, the Leverage Freedom Chair, which I worked on with Sudipto as well when I was here at IIT Delhi. And then I want to talk about making things and some of the considerations that go into creating products, ideally creating products that will reach large scale in dissemination, as well as the making processes that you might do as a designer, creating prototypes and most critical modules and things like that nature. And then I want to wrap up today with another exercise that I want you to do, and I'll explain that some more, but we're going to be looking at some products and thinking about them from the context of a user-centered and technical perspective like we've been talking about over the last few days. So let's start with the LFC. All right, so let's start with the LFC. So this is the Leverage Freedom Chair, and it's a wheelchair designed for conditions like this village in rural India with some like rough terrain. And the main innovation behind the design is that if you grab the levers down near the pivots, you can push through a big angle every stroke and go fast. And as the going gets tougher, you can slide your hands up the levers and produce more torque and go up steeper hills or go through mud or sand. So with this very simple drivetrain, very simple mechanical system, our chair is about 80% faster than a regular wheelchair. It's about 40% more efficient. And when you slide your hands up the levers, you can produce about 50% more torque and 50% more force to the ground than you could with a regular style wheelchair. Every single moving part on this device is actually made from bicycle parts. And we looked around the world to find the most commonly available bike parts that you could even source in a village in India or Africa, so you could make and repair the chair in these rather resourced constrained settings. When you take the LFC indoors, the levers just pop out, they pull out of couplings, and they stow in the side of the frame. And this converts the chair to a regular, conventional pushroom styled wheelchair. So we had to design it small enough to fit through a doorway, a standard sized doorway. It had to be low enough to fit under a table or a desk. And we had to consider other mobility situations, like how could you get into a bathroom and get close enough to, this is a Western style toilet in this picture, but close enough so you could transfer off and be able to use the bathroom. And everybody you just saw in these videos is a full-time wheelchair user. So that's kind of an overview of what this product was. And now I want to tell you the full story, including a lot of the mistakes we made along the way of how we made this device, and also how it became a reverse innovation, how we sell this now in the US market as well. So going back to, remember what I was talking about yesterday about defining your design requirements and trying to find problem merit, right? Finding a problem that's compelling, that's worth solving. About, more than 10 years ago, 13 years ago now, I spent a summer working in Tanzania, and I worked for a wheelchair organization there, and I worked for a company in the US that designed wheelchairs for developing countries. And they wanted to know what the current state of technology for wheelchairs was in Tanzania and how well it was meeting people's needs. And so I did a big survey of over 100 wheelchair users, wheelchair manufacturers, disability groups, and understood the current technology space around wheelchairs in Tanzania, but also that reflected challenges faced in other resource-constrained environments. And so what came out of that was, in my feeling, a compelling motivation for a new technology, a new product, in that worldwide, there's about 60 million people who need a wheelchair but don't have one. Most of these people are going to live in developing and emerging markets, and most, about 70%, are going to live in rural areas. Why that creates a challenge is, imagine you have to go a kilometer every day on a rough dirt road from your home to a school or to your work, and imagine pushing it in a conventional style wheelchair. It's really, really difficult to propel on those rough conditions. And so imagine the guy in the upper picture having to go on that soft gravel for like 1 kilometer. It's really challenging. And then if you look around the world, around the developing world, what's actually more common is hand-powered tricycles, and you have variants of this in India as well. And these work very well in urban settings, but they're too big to use in the home, and they're typically not geared to go on rougher terrain. They're geared to go on high speed on smooth terrain. So this started, making me realize maybe there's an opportunity here for an improved product for this space of particularly rural areas of developing and emerging markets. So one of the other first initial steps I think that was important was to look at what technology already exists for rural or for rugged terrain wheelchairs that could maybe operate in rural areas. And there's products on the market. The top picture is called the Renegade wheelchair. It's another lever-powered wheelchair, and it goes pretty well off-road. The bottom picture is called a one-off hand cycle, where you lay in a prone position and pedal the bicycle. But the problem is these type of products that are sold in the US are minimum $7,500. And the price point of developing world wheelchairs is an order of magnitude lower than that. So I was in this situation where I couldn't easily adapt existing technology that I'd buy maybe in the US to this condition in developing and emerging markets. Now, what was further interesting as we dug into this was looking at the design history in this product space. And so this is a selection of common wheelchairs that you would find around the world. Actually, the Jaipur foot hand cycle, that's an Indian one in the lower right. And so as I looked at this technology space, I realized that there was three classes that I saw of mobility products that were currently on the market. The first column is wheelchairs that were designed by Western engineers in the US or Europe and that are mass manufactured in China and shipped all over the world. There's products that were designed by Western engineers and locally made in local workshops in country. And then there was products that were locally designed in developing and emerging markets and also locally made. And what stood out to me here is that when I looked at all the variants that were designed by Western engineers, they all looked like normal wheelchairs. They all used push rims, where you grab the rims on the wheel to propel yourself, right? And what's interesting is if you contrast that to what was locally innovated, they all look like hand cycles. And so this stood out to me that maybe there's a mismatch or a disparity between how needs are perceived and designed for by Western engineers versus local innovators in these countries. And so this kind of clued me in that maybe there's an opportunity for innovation here. Furthermore, if we go back and look at the first patent filed for a wheelchair in the United States, filed in 1869, it's based on a similar platform to one of today's wheelchairs, where you have a big wheel in the back and a smaller wheel in front, and you grab the wheel to push yourself. And so I looked at that and saw, the platform hasn't changed much. Maybe there's some new thinking that we could inject into this new platform. So this enabled us, doing this background research. I spent a lot of time in country. I researched this situation worldwide. I understood the compelling need for wheelchairs around the world. This set up those core design requirements at the beginning of the project. That ideally we could create a single mobility aid that would go fast and efficiently, both on rough terrain, like in a village setting, like you see here, but is also small enough to use indoors. It's repairable, even in a local context, with local tools and local materials. And it has a price point of less than or equal to $250, so it's affordable within the current purchasing mechanisms of appropriate wheelchairs in developing countries. Now that last point has turned out to be more challenging than we realized because of the segmentation of the market and how wheelchairs are purchased. And we're going to talk a bit more about that before. But at this time, this was about 10 years ago now, a little more than 10 years ago, the other wheelchairs that would be used in a developing world setting that would actually provide a user a good experience, not like a really crappy hospital chair that might break in a condition like that in a few days, but like a more rugged chair. The price point was around $300, and we wanted to beat that price point or be around it, and that's why we set that design requirement. So going back to this price performance curve that I showed yesterday at the beginning of the presentation yesterday, we found ourselves in exactly this situation where we had a quite diverse existing technology space of many different wheelchair variants. And so, here's your $7,500 chair. Here's a sports wheelchair that you buy in the US. This is maybe around, a few $1,000s. Here is an appropriate developing world wheelchair that's pretty rugged. It's around $300. And then this would be a lower quality, mass manufactured, like Chinese wheelchair. It has like injection molded wheels, and it's maybe not designed for the rugged conditions in a developing country. And so we found ourselves in this situation where we could not see a way to just modify existing technology to somehow get down to the price point we wanted to hit in developing countries. We wanted performance similar to this off-road wheelchair, but at a price similar to another developing world wheelchair. And that made us realize that there was no way to adapt existing technology to get to where we want to go. We had to somehow disrupt. We had to think of something new, something that provided relatively very high performance, but at a much lower cost than other products on the market. So let me tell you about how we got there. So I thought about this engineering challenge for over a year. After I set out those design requirements, started thinking about this project, and what kept bothering me was that we needed something akin to like a mountain bike, but for your arms. Something that would give you a low gear to like climb up hills or go on rough terrain, and a high gear to go quickly. But the challenge was we wanted to do it in a package that was relatively low cost and quite rugged and robust in a resource-constrained setting. And the big innovation behind our drivetrain, what we realized, is that we could have a lever system where you grab a set of levers and you can change your mechanical advantage by just changing your hand position on the levers. So this would be a low gear situation where you produce a lot of torque on the lever because you grab high on it and you have this whole lever length L. And this would be the high speed, high gear situation where you have a smaller lever length, but you can push through a bigger angle every time you push to create a higher angular velocity. And so we could relate how fast you're pushing with your hands to how fast the chair would move just by a function of the drivetrain geometry. So as a function of the diameter of the chain ring, which is this big gear right here, the radius of the wheel, the diameter of the free wheel, which is the ratcheting gear back at the wheel, and this effective lever length. So this was a big insight for us, and it enables us to do a number of things. That one, we were exploiting a natural motion that a person is able to do, and as a result could have a very simple mechanical system. So a person can very easily grab at different points on a lever. Like we don't even have to think hard about it. But think about a mechanism that would like replicate what your arm is doing when you're grabbing. And on a regular bicycle, what does that is like a derailleur. A derailleur is what shifts the chain to different cogs. The problem with a derailleur, particularly in a resource constraint setting, is it's a rather fragile element, and they're also quite expensive when you buy them in developing countries. So instead of putting the complexity in the machine, we put the complexity in the person. So the machine could be just a simple assembly of bicycle parts in a single speed. So we're not shifting the chain to multiple gears. The second is this platform gave us a 3-to-1 change in mechanical advantage. So the lever length here is about 3 times longer than the lever length in the high gear. So what this gave us is, a big range of torque that we can put to the wheel. But to put it in another perspective, the best mountain bike components on the market that you can buy will give you about a 6-to-1 change in mechanical advantage, and they cost $2,000 per set. We use less than $20 of bike parts and get half that performance. So as far as price per performance, we're doing pretty well with this gear train. This is also more of a change in mechanical advantage than what you get on like a 10-speed typical bicycle, like a more simple multi-speed gear train on a bike. And then the final point about this architecture is that we could build it around a normal wheelchair and provide seating and postural support so a person doesn't lose their posture and slump down and maybe compress their lungs. And we could provide a cushion so they have support under their butt so they don't get pressure sores. And I bring this up because, and you're going to see where we made mistakes in this regard later on, but I bring this last point up because I'm talking here about additional requirements beyond the mechanical function of the device. Something I want to impress on you, and I saw this a little bit yesterday when we did the exercise, that I think all of us, me included, are much more comfortable with doing engineering calculations. You know, like I did the derivation of how to size the blades and everything, and I think all of you really got that and you thought about sizing down the blades. But what's harder to think about is like, let's envision like the hand-powered blender sitting in someone's kitchen. Let's think about how does that look? How does a person perceive that? How do they interface with that? You know, these are secondary requirements which can make a product successful or not. And in this case, so are these like seating and postural requirements. If the wheelchair develops pressure sores for a person, it can kill them, right? And it has nothing to do with its off-road drivability. So you're going to see some more of this going on. So being, I think, a diligent engineer, I was a grad student at this time at MIT, and I actually did this project as an independent study, and I thought about, could we optimize the drivetrain for a person's propulsion and performance? And so I did a very simple power balance where I said, and it's very akin to what we were doing yesterday, where you have a certain power source of a person putting power into the levers, and that power is going to be consumed by air drag, rolling resistance, and potential energy changes if you're, say, going up a hill. So you can write that as a very simple expression of the velocity of the wheelchair times the forces of drag, rolling resistance, and gravity. And then you can write an expression for air drag as well as the rolling resistance, which is depending on the coefficient of rolling resistance, mu roll, and the potential energy change if you're going up an angle. So what I was able to do then is do some research and figure out how much power could we reasonably get from a person pushing with their two arms. And what we were able to find is that if a person's just chugging along, not with their peak power, but just going along at a comfortable pace that they could do for about an hour with reasonable effort, with about I think it's a 20% increase in heart rate from resting, you can do, like an average male can do about 20 watts out of their arms with a pushing force of about 60 newtons and a hand speed of 0.38 meters per second. So what I was able to do then, and oh, by the way, I found this in the literature. This is another good point that like we did not have to reinvent the wheel here. We actually found a study on somebody else who did a lever power system and took measurements of multiple people so we could back calculate that power estimate. And so what I did then is said, okay, if I have 20 watts of power to use here, then I can solve for this equation for how fast I should be able to go, v chair, as I change rolling resistance and the climbing angle. So this is a strategy calculation. There's no picture of a wheelchair here. The strategy, there's some picture in your mind of a lever system, but I haven't designed a wheelchair at all here, but I've been able to do a calculation of how fast should the wheelchair be able to move as I change climbing angle and rolling resistance, simply through conservation of energy, right? I don't have a specific drivetrain designed at this point. I'm just saying I have a power source and I have a power sink. And so what was cool about this is that we saw that on relatively flat, smooth ground, rolling resistance around 0.01 or so in like 0 degrees climbing, we're hitting a speed of around 2 meters per second. That's 5 miles an hour. That is a fast walking speed. This is a pretty quick vehicle. So this was encouraging to us that, wow, this could be actually a pretty quick vehicle with this limited power source of your arms. And to put that in contrast, remember yesterday we were looking at human power? You can get 200 watts out of your legs for an hour, right? Most of you could do that. But now we have 1/10 the power, but we have to somehow achieve similar mobility. How do we do it? And we did it through this engineering. The other factor we had to think about was if we get into a really tough situation with tougher terrain, how much force could we push out, like doing like a bench press, in order to produce a lot of torque to get through like sand or mud? And what we actually ended up using as a benchmark of pushing force was US Air Force data from pilots who had to grab a stick and push it to control like the rudder or the elevators on the stick. So it was a very similar motion of going on a lever, right? So it was a reasonable ballpark estimate that we could use in our calculations. So then what happened is we took this speed map of how fast the wheelchair should be able to go at a given hand speed, and we wanted to design a drivetrain ratio that would give us the best conversion of hand speed to wheelchair speed. So we took this speed map of how fast the chair should go, given the power we have available. We looked at the terrains we might want to travel on, so ranging in rolling resistance from like smooth floors like this would be around 0.01 to like mud or snow would be around 0.45, and up to maybe quite steep climbing angles. We had to think about what are the parts available that we could use in a relatively simple drivetrain. And so at this point we were thinking about bicycle parts, and I did a survey on what sort of chain rings and freewheels could we find that could go into this wheelchair. And then finally, we had to understand how big the user is and how much of a range could they reasonably grab with their hands. Because somebody can't grab like a lever way up here, and even though it's a long lever, you can't push very well with your shoulder. You're strongest, doing a bench press motion. And so if you go much above your shoulder height, you get a lot weaker, right? So really it's from here down that we could figure out. And I had to realize that this is a guy in Guatemala. If he was standing next to me, he'd probably come up to here, right? I'm a pretty tall person. If I design just around myself, the chair's probably not going to work as well for a guy like that because he's shorter. So we put all of that together and use these calculations to understand as we change our lever length and change the torque output to the wheel, can we produce enough torque to overcome the rolling resistance or the climbing resistance? And so what we were looking at here is, at our peak efficiency, we were producing less torque, but I was able to calculate that if we change our lever range from about 20 centimeters to 60 centimeters, we could match the torque being imposed by the terrain of climbing angle and rolling resistance. Air resistance at these speeds is negligible. And I was able to calculate in that green band that lever range of 20 to 60 centimeters would allow us to operate at our peak efficiency in common driving situations. So that rolling resistance would correspond to like smooth terrain like this, all the way to like a gravel road would be about 0.1 coefficient rolling resistance, and a climbing angle up to about 6 degrees or about a 10% grade. So this was encouraging that in most situations where you drive, this wheelchair should work pretty well. Then we did the same thing for using half of our peak hand force. We didn't account for the full one. We looked at half if you needed to just put in a good amount of effort to get yourself out of trouble. And what we realized is that same lever range of 20 to 60 centimeters would get us through much higher rolling resistances and produce enough torque to go up much steeper climbing angles. So the punchline in all of this, the message I want you to take home, is that because we did this analysis, and I haven't shown you a picture of the drivetrain yet, like I haven't designed it at this point. This is just energy in torque conservation, right? I was able to see that 20 to 60 centimeters should enable us to operate at our peak efficiency in common terrains and produce enough torque to get through really rough terrains. So I talked about why we use bike parts, right? Like why we were so focused on bike parts, because they're so easily available. And this is, you see conditions like this throughout India too. You have a bike mechanic on the side of the road. I always see tire tubes hanging off of trees here. That's like the advertisement for a bike mechanic in this country. I love it. But you can go to a guy and he's got tools like this and he can fix your bike. And then just another little bit of reflection on bike parts. What's really cool about the parts that we use is that they haven't changed for well over 100 years. So what's called the safety bicycle, which is our conventional bicycle platform, this is what it looked like in the late 1800s, and then these bikes are still made in India, in China, by the millions, hundreds of millions now, which is pretty cool. So we were able to use those standards. They've been around forever. They're made by the millions, and you can get them everywhere. So, okay, back to the design process. At this point, this was back in 2008, so 11 years ago, we were at the concept phase, right? Using the same vernacular that we were using yesterday. So we had to start thinking about what is a physical embodiment through which we can grab lever ranges and propel this wheelchair. So here's a relatively simple concept. I'm just showing the person, this would be kind of a top-down view of the device, the person's interaction with the wheelchair. And at this time, we're thinking that the wheelchair would have two configurations. One would be regular wheelchair mode, where you just grab the push rims and you push yourself just like a regular wheelchair, and you have a big wheel in front and a big wheel in back and a small wheel in front. And then the other configuration would be like the off-road, all-terrain wheelchair. And what we would do somehow, we hadn't figured this out yet, is spin around the seat, so you now have the big wheels in front and the small wheels in back. And you can kind of use the big wheels to like climb over obstacles and go over like ruts in the road. So we like this concept. We made some bench level prototypes. This is a relatively simple prototype. This was with a wheelchair, this guy in this picture is a wheelchair manufacturer in Zambia from the target market that we're trying, or a representative from the target market we're trying to design for. So we're getting his feedback. And then we took the obligatory proud student picture. You know, colleges like IIT Delhi or MIT love pictures like this where their students make something, they're proud of their students, they want to show it in the media. And so we were really excited about this device that we had made, and we'd ride it around campus, and it was really fun. We were really excited about it. And then that summer, we made some more refined prototypes that had a lot of adjustability in them. You can see like this footrest you can adjust back and forth. It had a brake on it, so you could pull the lever back to stop the brake. And we ended up making 3 of these, one in Kenya, one in Tanzania, and one in Vietnam. And we made them with wheelchair manufacturers. We got their feedback. We had some wheelchair users get into them to get their feedback. And the consensus from all these people was that this device was terrible. It was absolutely awful. And I'm showing you this because another thing I told you yesterday is fail early and often. I did all those calculations in the spring of 2008. We made those the first prototypes in the summer. In the end of the summer, we went to the field and tested this and failed in context with people who know wheelchairs really well because they make them and use them, and understood why it doesn't work. And the reasons why this was so terrible is, one, it was impossible to get in and out of, right? Imagine if you have a spinal injury and you have to somehow crawl up over those footrests and get down into the seat. So it was really arduous to use. The second is this was incredibly heavy. This prototype was like 50 kilograms. It was insanely heavy for a wheelchair. Third, it was kind of really dangerous because when you went downhill, because you experience more drag at the front wheels than the rear wheels, and your center of mass is back here, it's like an inverted pendulum. It wants to flip around backwards, right? And we actually put some trail on this wheel. We put the swivel axis on this caster at an angle to try to make it more stable so it wouldn't flip around backwards. But it was awful. But the point here is that we learned it was awful pretty quickly, and we learned from the people why it was awful, who really know about the problem, and we worked with them to make it better. So at this point, this is an interesting, just an aside here, well, I'll talk about this product actually. So after the summer of 2008, we went back to MIT, and we started thinking about how can we make a different platform that is much more usable, much more familiar with people, and actually offers better postural and seating support. And so you can see that this prototype is like a normal wheelchair. But again, this is a proof of concept prototype. Look at how rudimentary this thing is. It's actually a plastic seat that I stole out of my mother's workplace. In their cafeteria, in their canteen, they had these chairs with plastic seats, but a metal frame underneath that we could weld to. So I didn't really steal it. I asked her if I could take it, but I took it, and we cut the legs off, and we welded it to this relatively simple steel frame. And we had the lever drive and the chain drive here. These are some mountain bike wheels. And you can see this is capturing the essence of what became the Leverage Freedom Chair, but it's a really simple prototype, right? And I rode this thing all over the place at MIT. I would ride it many, many days, go far distances, and I was empathizing with users. I was trying to replicate the experience a person would have to feel like, is this chair fast enough? Does it go through the right terrains? Where does it get stuck? Where does it break? And so one of the interesting asides here is in why I'm asking where the biggest loads are, is, well, I'll tell you in a second why that was so important, but can you guess where the biggest loads are in this chair? Where are the highest forces? Where would you guess? In what? No, it's not in each case. It's just, when you're using the chair, where would you, what part of the system experiences the highest forces? What? No, not the axle. The axle's supporting most of my weight and the chair's weight. So there's a few 100 pounds of load on the axle.
Actually, the smaller wheel, it will get stuck.
The what?
The smaller wheel.
No, not the highest forces there. There's actually very little load on this small wheel, because my center of gravity is about here, which is very close to the wheel axis, right? So as I extend this farther and farther and farther to produce, the restoring torque to keep the chair up, you need very little load there.
On the back side, the chair's back side.
The back? Nope.
The lever connecting to the...
Not the lever. Close. I'll tell you.
Chain.
It's in the chain.
Chain. Yeah.
So I'm a pretty big, strong person, right? I can push with, reasonably easily 200 pounds of force, right, in my arms. And so we're getting closer to 1,000 pounds of load in the chain, right? Quite high. If I'm really pushing hard, let's say it's 100 pounds and this is like, this lever was longer. This is about a 4-to-1 difference. Or actually, sorry, look at this radius here to this lever length. We're talking closer to 10-to-1. It's around 1,000 pounds, right? What we realized is that this chain tension would actually warp the frame. It would flex the frame and the chain would fall off the drivetrain. So again, doing these bench level prototypes is helpful because we ended up putting this strut right here in the frame, which supports the axis of rotation here of the chain ring and make sure it doesn't bend backwards towards the wheel when a huge tension gets into the chain. So just a cool aside from a machine design standpoint, like why we had to think about that. And we're not like clairvoyant when it comes to this. Like we didn't realize this until the chain started falling off all the time and we were like, why does it keep falling off? And we realized, oh, we're flexing the frame because of the high loads of the chain. Okay, another question. Why did we choose 3 wheels? Normal wheelchairs have 4 wheels. What could be better about 3 wheels? Exactly. Yeah. Yep. When you have rough terrain, yep. It doesn't matter how rough the terrain is. 3 points of contact define a plane. So we'll always have 3 points of contact with the ground. A 4-wheeled wheelchair can have a difficult situation where if like one of the rear wheels lifts up because the other 3 wheels are in contact, you lose your traction. So it's like a table that has one short leg. It's always kind of rocking. So that's why we went with 3 wheels. Also, the secondary reason is it enabled us to use a bigger front wheel and a longer wheelbase. So the longer wheelbase reduces the load on the front wheel, and that reduced load as well with the radius enables you to go over obstacles more easily, right? Okay, so at this point in the project, now we're in 2009, we started embarking on what I'd say were more organized field trials. Like the first one was just kind of ad hoc. We got some feedback from 3 organizations, but at this point, for the next few years, we really focused on some more diligent field trials to refine and really prove out this idea of if this would be an effective mobility aid. And we did this first in East Africa, then in Guatemala, and then finally when I lived here in Delhi, based in India with 25 people. Okay, so another just interesting machine design question. What do you think is a critical structural calculation in this design? And I want you to think of both like what would break, but also how could it affect somebody? What is a load calculation that you'd want to do? Well, and so that's a good point. I already told you that you have the highest loads in the chain. Let's say you shear a tooth off the chain ring, or your chain falls off. What happens to the user? Nothing, right? They're fine. It just turns into a regular wheelchair. They just grab the wheel, grab the push rim. So no big deal. Yeah, seat failure is one interesting one. The loads in the scene aren't tremendously large. Maybe I'll give you a little hint. Where do you think the highest stress could occur in the frame? Exactly. This is the only cantilevered structure in the whole frame. The rest of this, you'll see in some later pictures, the rest of the frame is trussed. It's all a series of triangles. But this is cantilevered. So right here, even though the loads are rather small on here, we have a long length here. And so we had to think about the bending stresses in here. And so why did we choose? You see the cross-section of this tube? It's rectangular. Why did we choose that? Yeah, exactly, a high moment of inertia. Right? So we had to think about that. This has a factor of safety of about 5 compared to static loads. So you can put like 1,000 pounds or 500 kilograms in the seat, and the chair is plenty strong enough to handle that. So we had to think about those things. Okay. So, as part of that too, you already pointed out the rectangular cross-section. I had to go to steel suppliers in East Africa to understand what steel could we actually get so we could choose a relatively high strength to weight ratio box section of tubing. So rather big, height of the tube and thin wall thickness. So here's just a zoom in of these, 2 by 1 by 1.2 millimeter thickness box sections. So yeah, I had to do that. I went to steel suppliers to figure all this out and design that frame. Okay, so in 2009, we went back and did our next field trial. And we made this variant of the chair, which was kind of a more refined variant of our bench level prototype that you saw me riding around at MIT. And we had 6 people in this trial, 3 of whom were full-time wheelchair users. And we realized that was really our target market, whose needs were underserved. People who ride hand-powered tricycles in a city, and let's say they had polio, and they can move around on crutches for short distances, but they just need their tricycle to go long distances. That product works pretty well for them. But the people who were underserved were people like this guy who had a spinal cord injury and had to go longer distances on rougher terrain. So I'm showing you data from those 3 full-time wheelchair users here. And so what we did in this trial is we gave these people leverage freedom chairs, we had them test them for 4 months, and then we came back and asked them survey questions to rate on a 1 to 5 scale how well the wheelchair did, our wheelchair, the LFC, and their conventional wheelchair, how well they performed in different types of terrains, going from smooth indoor terrains, level terrains, all the way through rougher variants, all the way to off-road terrains. And what was interesting about this study is that we saw that, yes, in off-road, rougher terrains, the LFC scored higher, did pretty well, but in indoor terrains, it was terrible. It was absolutely awful. And again, this is a story trying to tell you about failing early and often and why that's so powerful, and failing with people who can tell you why you failed. Because all 6 people in this trial said, the wheelchair is too wide. It will not fit through my standard doorway. And so this was an example where we were very enthusiastic engineers. I think we did a good job engineering this as far as like strength to weight and picking the drivetrain gear ratios and everything and mechanical advantage. But we forgot about this secondary requirement that a wheelchair is a chair that a person sits in like 16 hours a day. And for most of that time, they're not traveling any long distances. They're going to use our lever system maybe 1 or 2 hours a day if they have to go some long distance. As soon as they get indoors, they'll take the levers off and just grab the push rims. And when that happens, they need to get indoors. They can't stay outdoors the whole time. So we had not realized that important secondary requirement and had made a chair too wide accidentally. But we found out that, and we were able to address it in the upcoming prototypes. Next thing we realized is that the chair was rather tall, and people felt uncomfortable, like they could maybe tip over backwards if they tried to climb up a hill. And what exacerbated this is that when you push on the levers, you get a reaction force that's pushing you back, and that has to be supported by the back of the chair. Now, if we have a person with a spinal cord injury using this, they may have lost control of their abdomen muscles. So they can't react against it with their abdomen. And so if the back of the chair is too low and they're pushing really hard, their back is going to bend over the back of the chair. It shifts their center of gravity back, and they can flip over more easily. We had not realized this because me testing this, I have abdominal control. I didn't realize and experience that imbalance in instability. And then the third issue we found is that even though we thought about the steel sizes and everything of the frame, the chair was still too heavy. And all 6 people in this trial said, this chair is way too heavy for us to use. It's about 20 pounds or about 10 kilograms heavier than our standard wheelchairs. So we have to somehow make it lighter. And this is a significant challenge because our drivetrain weighs about 12 pounds. Right? It's pretty heavy, like all those mechanical components to drive the lever system. So somehow we have to make a lighter frame and a lighter chair. So this feedback is what's forced us to go back to the drawing board and improve the design. So we went back to MIT before we did another field trial, and this is kind of, I think, akin to what the Wright brothers would do. Instead of making a bunch more prototypes and sending them out to the field, we made 1 prototype or 2 prototypes at MIT and worked out these small issues like how do we make it narrower, lighter, more stable, etc. And so this is a very rudimentary prototype that's showing 2, I'd say, critical innovations that we created. The first is we went to a narrower tire size, which made the overall wheel narrower. We set the bearings inwards on the chair a little bit, but to leave room for the lever, we actually made the armrests start from the outside of the seat back, where you're wider at your hips, and taper inwards to the front of the seat, where your body's narrower at your legs. So this allowed room for the lever to swing and allow for the wheels to come in. Even though we made a narrower chair, we still had room for our hips. The second innovation that's in this very simple prototype is we had a seat back that we added. And this seat back supports you between your shoulder blades. It acts almost like a bench press bench. Like when you lie on a bench press bench, the bench is doing this same function of providing a reaction force at your shoulders. Right? So your back doesn't like bend backwards when you're benching. So it's much higher than a normal seat back on a wheelchair, and it's much narrower. It almost looks like a headrest, but it goes right between your shoulder blades. So we refined this, we rode these at MIT, and then the other thing we did is we started to get more quantitative in measuring the performance of this chair. So I actually made a data acquisition system, which a technician here helped me refine. It had some bugs in it. But this would enable us to go to the field and measure people when they were using the chair in context to measure how much power they were getting out, how much oxygen they were using, and actually show quantitatively how well the chair was performing. So at this point, we embarked on our second field trial in Guatemala, and we did all our testing in a rural setting on a rural road where a person might want to travel. And so we tested people with this oxygen system and power system, both using their regular wheelchairs and the LFC in these normal operating conditions. And so at this point, we were using an upgraded version of the product where we implemented these design upgrades that we had figured out over the preceding year. So here's the new chair, which was 3.5 inches narrower than our previous one we tested in Africa and was small enough to go through a standard doorway. And it's actually about within 1/2 inch wide. I think it's like 1/2 inch wider than a standard hospital chair that you'd usually use indoors. So it's about exactly the same size. We were able to lower the center of gravity by 5 inches in this chair through a bunch of tricks and how we designed the frame and the seat, and also we went to a smaller wheel size here to lower the center of gravity. And then here's that back pad. See his pushing and the force reacting at that back pad so his back doesn't bend backwards. This guy has a spinal cord injury. He has no control of his abdomen. And so that little back pad made a massive difference. And then also we were able to remove 20 pounds out of the weight of the chair by just, again, being very judicious about where we use steel. And this chair weighed 47 pounds which was almost exactly what the competitor chairs were on the market. So it was the same weight, even though it had 11 to 12 pounds of drivetrain weight. So we tested this in context in those videos that I showed you in Guatemala. And what I'm showing here is the velocity of the LFC versus the regular wheelchairs in that village setting. And so the chair was about 80% faster in that context. And then the bottom is showing a measure of efficiency in how fast the chair goes versus how much oxygen you're consuming. And so what we found actually is that people tended to exert themselves similarly on a regular wheelchair versus our wheelchair. So their oxygen consumption rate, their VO2, was similar. But in our chair, because it was so much faster, overall you're using less energy because you're running at that power level for less time. And so we represented this as velocity over VO2 as a simple measure. So here we're showing we're about 60% more efficient in traveling in these contexts. We also went back and did the same Likert scale measurements, asking people to rate the chair on that 1 to 5 scale. And so what we saw is really encouraging that the chair operated a lot better in these tighter indoor confined environments. And it was still measuring somewhat better outdoors, but what struck us is like, why wasn't it substantially better than a regular wheelchair? And you know how we figured out? We asked people, right? We were failing in context with our target users. And what we found out is that people said, boy, when I'm particularly going downhill and I'm pulling back on the levers, I didn't tell you this yet, but the brakes for the LFC are right here. These little orthogonal levers that come off the main levers. And so when you pull back, these rub against the tires and provide braking. But if you pull back really hard, you can pull yourself out of the seat. And so people said, I want to be restrained in the chair. I want straps around my chest and maybe straps around my waist and my feet so my feet don't come off the footrests and flop around. They also said the place where we had our parking brake was too high and that when you push really hard on the levers, you could smack the levers, you could hit them into the parking brake. So it was really disturbing when they pushed really hard. So we addressed all these challenges again when we did the next design, which we ended up testing here in India. And so in this prototype, you can see he's wearing a chest strap. And actually, he doesn't have them on, but you can see the foot strap right here on the chair. We lowered the parking brake by 4 inches, so it's down here on this little looped structure off the frame. So it's out of the range of the lever push. And so we went back and tested this with a number of individuals throughout India. And we tested it in their real world context of where they'd ride a wheelchair. And so here again, we saw that we were about 60% faster than a regular wheelchair and about 30% efficient. And I think these were the most telling and compelling data that we collected because all the people in this trial were just average people who had been injured, who had most of the time recently come out of the hospital. Whereas the people in Guatemala were actually on the national wheelchair team for basketball in Guatemala. These guys were all pretty good athletes. And so they were better at maneuvering wheelchairs than I think average people, but these were all average people in India. So we were like, at this point, we felt really good that these data are really legit. This is our real target market. And we have something here that's providing value to people. And what also indicated that is the survey results we got at this point. So again, here we're asking the same questions that we did in East Africa all the way through to India about how well the chair does indoors. And at this point, it was about as good as a regular conventional wheelchair that you get in India. And then off-road, look at the massive difference that the chair was able to do. It was much, much more capable on rough terrains. So at this point, too, I worked with the Jaipur Foot Organization while I was based here working with Sedipto. And so they're the ones that partnered with us to help do that last Indian trial, as well as a company based out of Indore called Pinnacle Industries. They made all our prototypes and eventually went on to make our developing world variants of our chair. And we built a company. We started a company around all this called Global Research Innovation Technology, or GRIT. And they ended up selling this, the Leverage Freedom chair for a price point of $250. That was if you bought it at bulk. If you bought individual chairs, it did cost more. But this product was the launching point for this company, GRIT. Now, I want to go back to this circular diagram I showed you yesterday because this project was another example of how we had to identify this chain of stakeholders that could get us from an idea to implementation in the real world. And so we certainly worked with end users a lot in this project and had to get their feedback. Then in the innovation phase of this project, it made a lot of sense that academics were working on it. We had facilities to prototype and test and measure data. So I did that at MIT. I did that while I was sponsored as a postdoc through the Singapore University of Technology and Design, SUTD, as well as here at IIT Delhi with Sudipto. Then you will often find that there's a massive gap between an academic prototype and a commercial product. And so we had to bring in resources in order to bridge that gap. And so we started GRIT to do that, but we also worked with a product design consultancy, Continuum, to help us productize this thing. We had to figure out how to commercialize it, and that was important to bring in Pinnacle Industries, what became our manufacturer. And then it was also important to work with organizations that disseminate chairs, Jaipur Foot. So again, I want to encourage you that when you start a project, I think being at an academic organization, you often operate right here, and you often focus right here. But I want to encourage you, think about the rest of this path. Think about how you're going to get back to these people. And is there a way that you can interact with these other organizations that can help get you there? Because each of these organizations is going to assert their own constraints and requirements that you also have to satisfy. So, as far as how the chair worked out, I'm going to show you a video now from one of the people in our last field trial in India. And this guy is named Ashok, and he's a tailor. And I'll let him tell you what happened. Whoops. I don't know why this... There we go.
ये वाली व्हीलचेयर दी गई थी फिर उस टाइम पे मैंने ये व्हीलचेयर ज़्यादा यूजेबल तो थी नहीं मगर मैंने ले ली मैंने कहा चलो ठीक है कुछ काम आएगी इससे कुछ काम आएगी फिर उन्होंने कहा कि इससे आप बेड पे आ सकते हो बेड पे से नीचे आ सकते हो इधर उधर कहीं जाने की हो तो इससे बैठ के जाया करो मैंने इसका यूज लिया नहीं था फिर ये दूसरी वाली ये वाली चेयर दी है आपने जब इसके बाद तो फिर मुझे से वहाँ से आया हॉस्पिटल से आने के बाद मेरी मत हो गया आपने भी कहा कुछ काम किया करो क्या करते थे हाँ फिर दूसरे दिन से मैंने यहाँ आया घर आया एक दिन रेस्ट किया फिर उसके नेक्स्ट डे मैंने ये दुकान वापस आ गया था यहाँ पर हाँ फिर दुकान डालने के बाद तो फिर अब रेगुलर.
So, as an engineer that, who designed this, that's really gratifying to hear a response like this. It is a single data point, right? This is one person's anecdote. But let me give you some statistics of that last trial. So we had 25 people in the trial. 11 of those people were full-time wheelchair users, our target market. We also had tricycle riders in the trial. And like I mentioned before, this really isn't for a person who already successfully uses a tricycle, like particularly in an urban environment. Tricycles are much faster than our wheelchair, and those people typically can go short distances under their own power, like with crutches. But for our target market of wheelchair users, of those 11 people, 10 of them adopted the LFC as their primary wheelchair. When they were using a regular wheelchair, none of them could travel outside of their house without the assistance of a family member. But with the LFC, those 10 people averaged independent travel of 2.7 kilometers per day, and 4 of those people were able to get employed again, like this guy Ashok. So those were compelling data for us, that we had something of value here, that people liked, they were utilizing it, they were excited about it, and that it could actually benefit their lives. And at this point, we were confident we had hit this mark, that we had made a product that was $250. It was a little bit lower than the price point of this chair, and it actually, I would argue, exceeds the performance of this chair because you can use it indoors. That Renegade wheelchair you could not use indoors. It was strictly an outdoor wheelchair. And ours was actually faster than that Renegade wheelchair as well. So we made this high value, high performance, low cost solution. Now, I think we got a lot of recognition for this that indicated we had created something innovative. So we ended up winning many of the national design awards in the United States for this product. And it also started cluing us in to an opportunity of could we make a variant for the US European market? So what happened is that as we started getting some press about this, some newspaper articles and TV coverage, wheelchair users in the US and Canada and Europe started contacting us and saying, why would you only make a high performance, low cost, all-terrain wheelchair for developing countries? We want that too. We would love something robust like this, and we can go in rough terrain and we can repair it locally. These same features that you incorporated into the wheelchair for the developing world, we could benefit from too. So what was interesting to us is we had never anticipated or planned to make a US version of our chair, but consumers were telling us there could be value there in doing that. So we embarked on an effort to figure out, is it possible to make this US wheelchair? Could it be valuable? And maybe what would we change about it to do this reverse innovation process? So we started with this collaboration with the product design consultancy I talked about a minute ago, Continuum, and they made what I would say was kind of the sexy concept car version of our wheelchair. Look at this thing. It looks futuristic. It looks awesome. It's very aspirational. It's also completely not functional, right? You look at it just closely from an engineering perspective. What holds most of the weight of the chair is your CG being near the rear axles. So they put in this shock absorber here, right? But all that's going to do is as the front wheel goes over bumps, it's going to compress the shock and make the seat back move back and forth, right? So this was a valuable exercise, and I think got people excited about the project. But in hindsight, I think it maybe led to some consumers being disappointed that the eventual product that came out of this effort didn't look as sexy as this. And also this was a bit misleading because it wasn't functional as an engineering piece of hardware. So we had to design an actual variant of what the US version would be. So the way we did that, again, was going back and getting information about the market. And we ended up doing a number of surveys, first in Singapore, at a disabilities exposition there. We did a bunch of web-based surveys for wheelchair users who had interacted with us. And then we also identified lead users. I talked about lead users yesterday. These are people who are kind of extreme, very knowledgeable users about a product that can give you really good feedback. And so we identified a program very close to Boston that does outdoor recreational activities with people with disabilities, and they actually use off-road wheelchairs. So we were like, let's go test with them. Let's get their feedback. So we got feedback from 14 of their users. So what came out of that study was, the way we structured it, was we first had people weight their priority on a 1 to 5 scale, 5 being the most important, of features that they valued in a wheelchair. And so we found that lightweight and quality of life and reduced effort and portability were all really important to wheelchair users. And we did this first for people before they had seen the Leverage Freedom chair. We didn't tell them about it. We just said, look, just imagine the ideal wheelchair, right? What would you want out of it? And that's how they rated these factors. Then what we did is we showed them the LFC. We showed them videos, we explained what they did, and asked them again to report what are the features that are important to you. And what was interesting that came out of this is that some of the merits of the LFC became higher weight priorities, like affordability, goes off-road, is serviceable by a non-professional like a bicycle mechanic, etc. And so it started cluing us in that yes, there is value in the LFC's features. Then the other thing we did is we looked at the distinct needs that were expressed by developing world wheelchair users in all of our past work, when people talked about repairability, affordability, etc., rough terrain capability. We looked at those needs and we compared them to the needs of wheelchair users, both expressed before they knew about the LFC, right? So these are just people saying, this is what I want in a wheelchair. Not necessarily the LFC, just in general, what they want in a wheelchair. And there was 13 shared needs that overlapped, but there was 9 distinct needs expressed by people in developing countries. These were the needs like off-road capability, lightweight, easy repairability, etc. Then after the LFC, After we prompted people and showed them the LFC, we also assessed their needs. And what was interesting is that these 9 distinct needs from the developing world transferred into the shared needs set. What this indicated to us is that people in the developing world were actually acting as lead users. They were identifying latent needs that people in the US and Europe weren't able to identify. Valuable features that could make a valuable product that your average person in the US wouldn't even think of. And so this is a really important point, because you can sometimes identify population sets that are very insightful and can be lead users. And if you can get information from them, it can make you create a more valuable product, because you're going to create features that are valuable to a much bigger population. And that happened by working with people in the developing world, which was really cool to measure. We were able to see that and measure it quantitatively. So what came out of this study as well was mapping out actual features we had to include in the wheelchair to make it suitable for users in countries like the US. And the biggest one was portability. In countries like India, we found that most of our users, particularly in the village area, did not travel in cars on a daily basis. And if they had to go in a car or bus, they could put the wheelchair on top and it was okay. It was a reasonable way to transport. Whereas people in the US are probably going to use this more as a recreational device, like a mountain bike. So they want to be able to put it in the boot of their car, go to maybe a park or a national park or a preserve, and then take it out and use it. So we had to make the chair collapsible to fit into the boot of a car. So this required substantial more engineering effort to make what became a quick release axle, where you could quickly just take the wheel off the chair. And we had to do a bunch of more analysis and testing to make sure the wheelchair was rugged enough and the axle system was rugged enough. So this is us, look at this, we're actually destroying this wheel here, because we have, these are all 45-pound weights, about 20-kilogram weights here stacked up. There's 4 of them, or 5 of them, so a lot of weight in the chair, making sure our axles are robust enough. Now, another important point here from a design perspective I want to stress on you is this Kano diagram. Have you ever seen this before? These are pretty cool diagrams. And so what this shows is how users will perceive different features of a product and how they'll respond to it. So in these 2 lines are important because we're talking about features that delight users and features that meet basic needs. So for example, when an iPhone came out with a camera that faced you when you looked at the phone, that was a feature nobody ever had seen before. And it delighted people and they loved it. And when it was fully implemented, it made them very satisfied. But before it was implemented, they didn't even know about it, right? So they weren't dissatisfied. But to compare that to basic needs, imagine the brakes on your car don't work. Everybody expects the brakes on their car to work, but if you have substandard brakes, you're going to make people very dissatisfied very quickly. And like, brakes are always on a car. They're never really going to delight somebody. They're just kind of a basic need, and the best you can do is try to not dissatisfy somebody. Try to get as close to this indifferent zone as possible. So we had to think about this in terms of the LFC, because features like our lever system, that was really unique. And our price point. We had a very cheap product. That delighted people. They were excited about that. But things like the quick release wheels, so you could take the wheels off and put the chair in the boot of a car, those are standard features on a wheelchair. We had to do those. And if we hadn't, people would have been really dissatisfied, right? So this is something for you to think about, like what features are going to really resonate with people and get them excited, and what are just basic needs that you absolutely have to do. So what came out of this was this variant of the LFC called the Grit Freedom Chair. And you can see it shares the same DNA as the developing world variant. It's got 3 wheels, it's got a lever drive, it's got the back pad, but it has quick release wheels, it has a bit higher level of fit and finish, it's got like better mountain bike wheels and mountain bike tires, but it is the same DNA. And so here's that chair in action. And look at how this is being marketed. This is not a medical product. This is an enabling, off-road, go anywhere, liberating machine. It's like a mountain bike, right? So that's the Grit Freedom Chair. And what has happened now is that Grit has developed these two product lines. And another important point to make about this is we never set out to do like a, do you guys know the company Tom's Shoes? Do they sell those here? There's a popular shoe company in the US called Tom's Shoes. And whenever you buy a pair of shoes in the US, they give a pair of shoes in the developing world. It's a buy one, give one scheme. And we looked into that for this, but wheelchair users in the US are typically also pretty economically constrained. And they said, you know, we want to support people in the developing world, but we really are constrained ourselves financially, so we'd rather have a low-cost wheelchair. And what we set out to try to do, and I'll tell you some more about how we weren't as successful as we wanted to be here, but what we set out to do is make a business where we do high volumes and relatively lower margins in the developing world segment of the market, and this is the chair that was made in India. And then in the US market, do a higher price point and relatively low, higher margins, but lower volumes. And so this chair is doing pretty well. We're selling a good amount of them at a reasonable price point. And we're like less than half the cost of like other competitive products on the market. But we created this company that manages both those pieces of IP. And so I think, you know, we were successful in doing this reverse innovation. We did, you can see here again, same DNA, but different product, same product family, but different feature sets, depending on which market we're working in. So now I want to go into lessons learned, and I think this is a good time to stop the video, actually. Now I'm going to give you a bit of the inside lowdown and the rest of the story. So why don't we stop the video right here, and maybe, do you guys want to take a break right now? Good break time? Yeah, we can do 15 minutes. There's not much more to tell about the LFC. So we can go until the end or take a break. There's, let's see, how many slides?
You want to stop the recording, right?
Yeah, let's stop the recording. Yeah, why don't we finish up the LFC? And then we have a clean break for the next topic.
You have to indicate.
Yep, so I'm going to turn mine off.